Okay. Suppose we wanted to take the region bounded by x equals 0, x equals pi over 2, and cosine, and rotate it around the y-axis. How would we set up our integral?
First, we can draw the picture.
So cosine, there's pi over 2, right?
Although it doesn't really matter, I would suggest we do the top line. Just call it life easy.
Yep, to make life easier, go out there. We're going to have to use which method? Shell. So the integral from 0 to pi over 2 of 2 pi times
X. Cosine X.
Okay, we have x times cosine of x. We do not know how to integrate that. Okay. This is a reason why we have integration by parts. Okay. Integration by parts helps us take integrals of products that we can't use substitution for. Okay. So, let's talk about this differentiable product right here. We're basically gonna come up with the rule for integration by parts. Okay? So, U and V are differentiable functions of x. Okay? So when we take the derivative of this entire equation, what's the derivative of y with respect to x?
D by dx.
Okay? And then when we take the derivative of u times v,
U prime times v plus v prime times u.
so I'm going to write it du dx v plus dv dx u. And so then, what I'm going to write is dy equals v times du plus u times dv.
Were you using U and V's a lot?
Yep.
I'm curious.
Got a little calendar usually.
Yeah, make sure your u is kind of loopy. Okay. So now, what I'm going to do
With v's or w or with u times u.
is this. Okay. We're going to do a little rearranging. Okay. I'm going to keep u times dv on the right side, and I'm going to subtract the integral of v du.
Doesn't matter which one you do.
It does.
How will you be able to differentiate u from v in any equation?
I will tell you how to do that.
Addition.
Okay. Now, when we integrate dy, what do we get? Okay. Okay. I'm going to go ahead and flip-flop this. The integral of u dv equals y is the same thing as u times v. Do you agree? Integration by parts. The integral of u dv is u times v minus the integral of v du. You need to remember this. Now, what we're going to have to do is we're going to have to take an integral that's a product, and we're going to have to figure out which function is u and which function is dv. So then we can use this right here, okay? Basically, we're going to take one function to integrate and one function to differentiate, okay? If we have a u in here, we need a du over here, so we're going to have to take the derivative to get du. Whatever we pick for dv, we're going to need a v right here and right here. So whatever we pick for dv, we're going to have to take the antiderivative to use here and here. Okay? So within our integral, we get to take derivatives and antiderivatives, okay, for this to work out for us. All right? So we've gone through this work to write this rule. This is something that you need to remember so you can use over and over and over. Let's try it. We're going to go back to x cosine of x. Okay. So we need to pick a u, and so we can determine our du. And we need to pick a dv so we can determine our v. All right? All right. Zach is suggesting x and cosine of x. I do like to pick polynomials for u as much as possible. If you have a polynomial as one of your products, then making it u is probably going to be the best. Okay? So if u is x and dv is cosine of x, let's go ahead and I'm going to just, for reference, write up. Okay. So if u is x, what is du? 1 dx, right? And we're using differentials here. If dv is
Negative sign. Or sign, yeah.
all right. So going back to that red rule up there, the integral of x cosine of x dx becomes u times v x sine of x minus the integral of v du. V is sine of x, du is dx. Okay. We don't have to worry about that plus c right here because we're going to get it right here. All right. So we're going to get x sine of x minus the antiderivative of sine of x. Okay, so we get minus a negative cosine of x plus c. There's integration by parts.
That's it?
So we have to practice identifying u and dv so we can make this work.
We would find the answer if we chose u to be Cosinus.
Would we have gotten the same answer? Yes. Okay. However, well, here's the deal with that, Bailey. I'm going to maybe retract my statement. If u was cosine of x and du, excuse me, dv was x, then, okay, du negative sine of x and v would be 1/2 x squared, right? When we go to make v du, we're going to get stuck with the same problem where we have a polynomial times sine of x. Okay, so that's why I say if you have a polynomial, you need to put it as your u. Otherwise, you're going to run into needing integration by parts again.
So U should be a polynomial.
Is that what you're trying to have to do integration by parts within the integration by parts problem?
Yes. Sometimes it will not take, sometimes you have to do integration by parts multiple times. And we will look at all those cases, but let's just get integration by parts under control the first time.
Is there some kind of like concrete way to determine which is U and which is dV, other than like most of the time we want the polynomials to be U because, or which is U and which is dV because.
If there's a polynomial, you put it as u because we know it can differentiate out. And you'll see what I mean when we get to something that's not just x. Okay. Other than that, okay, there are a few different types of things that are going to happen, and we're going to look at those examples so you can see what to look for. Okay. Let's try this one. E to the x times x dx. Based on last example and what we know about x and e to the x, what should be our u? X. Making e to the x dx our dv. Okay. I don't know if I did a good job putting dx over here. I apologize. Forgot about that. You need the whole thing. Okay, so if u is x, du is 1 dx, yes. And if dv is e to the x dx, then v is e to the x. So our integration by parts, e to the x times x dx, u times v minus the integral of v du. So we get x e to the x minus the antiderivative of e to the x.
dx plus C.
I love e to the x because the derivative and antiderivative are so wonderful. Yes.
Is it possible to use integration by parts where it's not needed? Like, say for example, you had a polynomial similar to that, except like you said, e to the x and c to the x squared, so it still could technically work. Could you still
No.
use integration by parts?
No, because when we have e to the x squared, we don't have a way to integrate that without u substitution. If that was x times e to the x squared, you would want to use u substitution. Integration by parts is something to fall back on when you have a product that you cannot use u substitution with. U substitution you should still always look for first. Okay? So don't be caught off guard if there is a problem in your homework where you do have to use u substitution instead of integration by parts, because it is important for you to know the difference. Okay? x times e to the x squared will appear sometime this week. I can't remember when it's going to appear, but it will come back at you. All right. Now, natural log of x. You have never been able to integrate this. Okay? You don't know the antiderivative of the natural log of x. You know that the antiderivative of 1 over x is natural log, but we don't know the antiderivative of the natural log. Okay? We have to use integration by parts to do it. Okay? If we don't know the antiderivative of the natural log of x, the natural log of x has to be what? Our u or our dv? Mm-hmm. We can't put natural log here because we don't know the antiderivative. So the natural log is u, and then 1 times dx is dv. So what does this make u? du, excuse me.
1 over x dx. And d is equal to x.
And d is equal to x. So the antiderivative of the natural log of x is u times v. So x natural log of x would be u times v minus the integral of v du, right? v. What is that really saying? The antiderivative of 1. So we have x natural log of x minus the integral of dx is x.
Plus e.
Well, that's why we didn't have to memorize it.
This is one that you'll want to remember how to do. Okay? It's a little different than the other 2 examples that we talked about. All right. See it? Okay, e to the x times x squared dx. What's going to be our u?
X squared.
Which means dv is e to the x dx. Okay? Some of you can see what's going to happen here. du is 2x dx, and v is e to the x. So when we come here to do our integration by parts, u times v is x squared times e to the x, that's nice, minus the integral of v du, e to the x times 2x dx. Okay. I can't remember. Bailey, were you asking me about this, or was it Zach? Are we going to have to do integration by parts in our integration by parts? Okay? This is basically, okay, if we rewrite this, we have x squared e to the x minus 2 times the integral of e to the x times x dx. Okay? So then e to the x times x dx, we can't take that integral. So we have to do integration by parts again.
Okay, it's right above.
Okay?
If you're talking about.
I know, but let's pretend that we didn't do that. Okay? We would have to let u, and this is like for the second time, right? U would equal x, and dv would be e to the x dx, right? So du would be dx, and v would be e to the x, right? This is something that we did on a couple slides ago. So what we would have to do, coming back all the way up to there, so I'm going to just copy down what I have in green up there. Our original problem, e to the x, x squared dx, we said it equals x squared e to the x minus 2 integral e to the x times x dx. Okay, and so now we are saying that the integral of e to the x times x dx is now u times v minus the integral of v du. Oh, good, it's South Day though. Okay, so we had to do integration by parts 2 times. What if that would have been an x cubed e to the x?
3 times.
We would have had to do it 3 times. And what if I was really annoying and I gave you x to the 5th?
Okay.
We would have had to do it 5 times.
Is there a shortcut?
Yes. There is a shortcut. Would you like to know the shortcut?
Ooh.
Okay. If you have a polynomial as a part of your integration by parts integral, you can use the table method. I know. I'm making sure everyone has written down what they need to. Okay. A table will make your integration by parts go much quicker. It's more efficient. But like I said, it's only going to work if we have a polynomial piece. Okay? So you're going to make a D column, you're going to make an I column. D for derivative, I for integral. Okay. If we have e to the x and x squared, what goes in our D column? What would be our u?
X squared.
X squared. That's what's going to go in our D column.
Wait, so these are what now?
D is what we would put in for u.
Okay, so, okay.
Okay. And what we would pick for dv would be our integrate column.
Oh, that's what.
Okay. The D column, you are going to differentiate until you hit 0. What's the derivative of x squared?
2x.
What is the derivative of 2x?
2.
And what's the derivative of 2?
0.
Okay. And you're going to do the same thing, but you're going to integrate the other column. And the x, the x, and the x. We're not going to worry about plus c's right now. Okay. We will worry about the plus c at the very end. All right. Now, this is what we're not to remember. Okay. Every time we do integration by parts, we subtract v du, right? So every time we do integration by parts, we're subtracting a new integral. So our signs are going to alternate as we do each of these integrals because we keep subtracting, subtracting, subtracting. Okay. So then, to get each of your u times v, etc., you're going to match up diagonally. Whatever you have in the first row is going to match up with the second row. Second row to third row, etc., until you run out.
Multiplication.
It is multiplication. and then you add each of those products together. Did we get the same answer as before? Was it more efficient and more fun?
So when is that not gonna work?
If we had e to the x times sine of x, that would not work.
So whenever it's just a single,
Basically, if you don't have a polynomial to put in the D column, it's not going to work. Because a polynomial is the only one that's going to differentiate out to 0.
what are you classifying as a polynomial? Because it's just one term.
A polynomial is in the form of x to a positive integer power.
No.
And it could be x cubed plus x squared. I mean, that's still a polynomial. But we're probably going to see one term polynomials here. Does that make sense? You could see some two-term polynomials.
I think it was classified as a polynomial if it was only one.
But
If there's only one term.
okay, we could say that that's a polynomial. But what I'm saying is you could have polynomials with more than one term, so I'm going to say polynomial. And I'm actually going to change this example. Let's make that a cube. Because that's boring if it's x squared.
You make it a shortcut?
You tell me, can we take a shortcut?
Yes.
We sure can. Would you like to take a shortcut? Yeah. Okay, which one goes in the differentiate column? Okay, and so sine of x goes here. So x cubed, 3x squared, 6x, 6, 0, step. Please be careful, because we're doing antiderivatives in the right column. What's the antiderivative of sine? Negative cosine. The antiderivative of negative cosine. Negative sine. The antiderivative of negative sine. Positive cosine. And one more time. Okay? We stop when we get to the row with the 0. Positive, negative, positive, negative, positive, negative, etc. And then we match up our products with the next row. So the integral of x cubed times sine of x dx becomes negative x cubed cosine of x plus 3x squared sine of x plus 6x cosine of x minus 6 sine of x plus c. I did not write. Imagine having to do that with integration by parts 3 times, okay? You're gonna be a little frustrated. What? Okay, so on your gold sheet, whoa, good save. This is your homework. And look at that. It's 9:37. You have 10 seconds. Which I expect all of you to start it.
Always stable.
Tomorrow we're gonna look at what happens when we have e to the x times cosine of x.
Sadness, is sadness the answer?
I'm gonna assume sadness.
Oh, because we'll never get to zero.
That mission will
Oh.
always be just,